Hello again, this is Brooke Cologne from EL6303 with question 2 from homework 10. And as with question 1, which asks us to collect definitions of the properties of stochastic processes, I'm mainly going to be focusing on the second part, which is explaining your understandings of these processes. As again, these videos can be long and tedious if I try to put the definitions on, which you again can find in the lecture notes, and I don't need to necessarily repeat them for you. So we have about 8 of them, and we're just going to go down the list, except for the last one apparently, which is not required, martingales. So we're going to go through 7 of them. So first is the wide sense stationary process. So it only uses mean and autocorrelation, so they're generally easier to get than second order densities. And based on the mean and autocorrelation function, there are a lot of things that we can do, such as stating estimation, parameter estimation, prediction in the mean square sense. With regards to communication application, generally we don't care too much on a specific value of the stochastic process, and majority of effort is spent on the power of the signal. Autocorrelation function is RT1 and T2. For T1 equals T2, such as the average power of the signal at T1. Since we see that the input is a wide sense stationary process, the output of a stable LTI system is also a wide sense stationary process. So now for number 2. Independent increment process, meaning x of t1 minus x of t2 and x of t3 minus x of t4 on non-overlapping intervals are independent. And we can see so far that Poisson process, random walk, and Wiener process are independent increment processes. And it seems that independent increment property is somehow related to Markov process, which, okay, we're going to see in number 3. So in the Markov process, if a process of, such as x of t is a Markov process, we say that it is if the past has no influence on the future when the present is known. And generally with Poisson processes, Poisson impulses, semi-random telegraph, random walk, and Wiener processes are all Markov processes. And in the real world, again, as we just stated from all the different examples given, many processes have Markov property, and binary transmission is a discrete state Markov process, and we can call it a Markov chain. For normal processes, Gaussian, we can say that a process x of t is said to be normal if the random variables x of t1, x of t2, so on and so forth, all the way to x of t of tn are jointly normal if for any n, any t1, t2 to tn. That is, if f of x of x1 through xn and t1 through tn. Again, I'm not going to try to explain all this, but essentially it's the definition of what a Gaussian, it's the mathematical definition of what a Gaussian process is, a normal process. But essentially, the normal process, or the statistics of it, is completely determined in terms of its mean and autocorrelation. In general, the mean is a function of t, and we classified Wiener process as one example of stochastic process, and same goes for normal process, and meaning we treat normal processes as a larger class of stochastic processes and Wiener processes as a specific example. For the strict sense stationary process, a process is said to be that if its statistics are not affected by a shift on the time axis. So a strict sense stationary process requires f of x of x1 through xn, t1 to tn equaling f of x of x1 to xn, t1 plus epsilon, t2 plus epsilon, all the way to tn plus epsilon. For white noises, the Wiener process, if we want to discuss its derivative, which is v of t is equal to the derivative of w of t over t, just the derivative of w of the Wiener process. We say that the expected value of v of t is equal to the expected value, the derivative of the expected value of the Wiener process, and that is equal to 0. And let me see. If we have so let's say the Wiener process is continuous with a probability of 1, it has a differential, and it's Gaussian white noise with a 0 mean and impulse autocorrelation function. If we want to define more general white noise with 0 mean, I should say that we want to define more general white noise with 0 mean and impulse autocorrelation function. And a stochastic process is said to be white noise if the expected value is 0 of v of t, as it was defined earlier. V of t being the derivative of the Wiener process. As for the mean ergodic process, if a stochastic process, x of t, is said to be a mean ergodic process, if the limit as t goes to infinity is of 1 over 2t times the integral from negative t to t of x of t dt is equal to the expected value of x of t in the mean square sense. And again, generally we're mainly always talking about the mean square sense, which is me just saying that it's a consistency. So that's about it for each of these. Again, we're not considering the martingale process, so that should be about it. And again, if you have any comments, questions, or whatnot, or want to correct me on anything, by all means go ahead and leave a comment. So thank you.